Hello, everyone, and welcome. My name is Jennifer Nyman. I am a principal at Geosyntec Consultants in Oakland, California. I'm a facilitator of today's webinar on behalf of SERDP and ESTCP. The webinar today will consist of a brief overview of SERDP and ESTCP, followed by the technical portion of the webinar. It features SERDP and ESTCP award-winning projects in the Munitions Response program area. Dr. Stephen Cargill from the Applied Physics Laboratory at the University of Washington will summarize results from basic research conducted over a period of a decade to understand physical mechanisms associated with scattering sound from objects near a water sediment boundary. He will also discuss current efforts to transition the knowledge gained from an applied platform for munitions detection and classification. We will pause midway through Steve's presentation for a Q&A session, and we will conclude the webinar with a second Q&A session. The next several slides provide instructions on optimizing your webinar experience today. If you have not done so already, please download Zoom at the link shown here and provided to you in your webinar registration confirmation email. If you cannot download Zoom, you may view the slides using a compatible internet browser such as Firefox, IE, or Edge, and by creating a free Zoom account. If you are unable to view the slides if your screen freezes, try keying Control plus F5 to perform a hard refresh. If you are accessing the audio through your computer, you can troubleshoot the audio by clicking on the arrow next to the Join Audio button and selecting Test Speaker and Microphone, and then follow the prompts as they appear on your screen. If you continue to experience difficulties, please call into the conference line shown here. You may also submit a comment using the chat box. Please use that chat box, though, only for comments related to technical difficulties. We'd like to save the Q&A box on the lower portion of your screen for questions for the speakers. In case of continued technical difficulties, you can download a PDF of the slides from the webinar webpage and call into the conference line provided to you in your webinar registration confirmation email. We will also be live streaming the webinar on the SERDP and ESTCP YouTube channel at the link shown here. Today's broadcast will be listen only. You may submit questions by using the Q&A box on your screen. You do not need to wait until the question and answer period to submit your questions, and in fact, we encourage you to submit questions in advance of that session. When submitting your questions, please add your organization name at the end of your question so that we can identify you during those question and answer sessions. With that, it's my pleasure to introduce Dr. David Bradley, who is the SERDP and ESTCP Program Manager for Munitions Response. Dr. Bradley's professional career includes U.S. Navy-supported research, laboratory directorship at the NATO Undersea Research Center in Italy, and research and academic activities at Pennsylvania State University's Applied Research Laboratory. An emeritus professor of acoustics, he is currently assigned to the SERDP and ESTCP Program Office. Dr. Bradley is a fellow of the Acoustical Society and has chaired society committees and has served as president. Dave, please proceed.
Thanks, Jennifer. Welcome, everybody. And also from the office, I'd like to extend our best wishes and our hopes that everyone listening has been able to avoid the virus that's within the country today. SERDP, SERDP, I should be careful about trying to say the acronym, and ESTCP are joint programs. They're multi-agency programs with a focus on issues of the Department of Defense. SERDP is the researchy end of it and is more focused on the kind of work that you will hear described in detail by Steve in just a few moments. ESTCP is the other half of the program, if you will, and really relates to demonstration and use of techniques and ideas that are developed in the more researchy end of things in SERDP. As you would expect, they're complementary programs and there's overlap between the two, but in fact, they do have that separation. There's 4 program areas in SERDP. The slide you're looking at, the second one is only in ESTCP. The other 4, which include environmental restoration, munitions response, resource conservation and resiliency, and weapons and platforms, are the remaining programs. Specifically today, we're focusing on a munitions research and response program. Our mission, if you will, is when asked to remediate a site, is to go to that location, do the searching for the objects, munitions, etc., identify them, and what we would call localize them so they can be removed. So our end of it is the search and localization, and I'm really looking forward to Steve's presentation. The webinar series as a total, I strongly encourage you. I obviously have a bias toward munitions remediation and response, but I would urge all listeners to take advantage of the webinar series, because they're all very good descriptions, and they're exciting areas of research that are going on today. And I look forward to them myself, even though I work with them day to day. They're always a fun opportunity and a very informative one. You can find additional information in my final slide, at least, at that website. And you can also download Steve's talk today. And if you would please take advantage of the survey that will pop up on your screen at the end. Again, welcome, and I hope you enjoy the webinar today.
Excellent. Thank you very much, Dave. It is now my pleasure to introduce today's speaker, Dr. Stephen Cargo, who is the Senior Principal Research Physicist with the Applied Physics Laboratory at the University of Washington in Seattle. Steve's current areas of research include the scattering of sound from objects and wave propagation within marine environments. He has served as a principal investigator on several SERDP and Office of Naval Research grants and contracts, which address detection and classification of underwater munitions near a water sediment boundary. He is a fellow of the Acoustical Society of America. Steve has a bachelor's degree in physics and mathematics from the University of Dayton in Dayton, Ohio, and a master's and doctoral degree from the Washington State University in Pullman. Steve?
Thank you, Jennifer, and thank you, Dave, for the opportunity to speak today. The presentation is split into 2 parts, a basic research part and an applied systems development part. And I'll address each one of these bulleted items underneath the 2 parts as we go along. About 5 years ago, I was in a discussion with Herb Nelson, the then program manager for Munitions Response, and we had a robust basic research program going along, and he asked me, where were we going? And at that point, Kevin Williams, Aubrey Espana, and myself sat down and came up with a 5-year vision on how we could transition our basic research into an applied research program. Now, this is a flow chart of principally the last 5 years of what we have done. And what I'll be talking about today is highlighted in the green box, particularly year 3. And then in the second half, I'll be talking about the ESTCP MR18 B4 5004 program, which is how we are transitioning the basic research into an applied platform. project team on MR2505 was myself, Aubrey Espana, Kevin Williams, and then Dr. Jack McLaughlin. All of us are located at the Applied Physics Laboratory. Now, this work cannot be done in isolation with just 4 people. There's a significant number of collaborators that we've had either directly on our projects or they had complementary projects either funded by the Office of Naval Research or through SERDP or ESTCP. The important one here is the Naval Surface Warfare Center in Panama City. They have been a partner in all our experiments, and importantly, they have handled the environmental assessment that you need to have if you're going to go to sea and put sound in the water. I will apologize. I know this is not a comprehensive list of everyone we have worked with, and if your name's not showing, it's simply because when I was putting this slide together, I forgot. So I'm going to go over our at-sea experiments, and I'll be talking principally about CLUTTEREX. Our experiments were conducted in the Gulf of Mexico, just south of Panama City, Florida. The 3 experiments that make up our at-sea measurements are the BAYX experiment that occurred in 2014, the T-REX experiment that occurred in 2013, and CLUTTEREX, which occurred in 2017. The CLUTTEREX and the T-REX site are the exact same site. They're separated by 4 years. The way our at-sea measurements were conducted is a 42-meter long rail, and there's a picture of only 21 meters of it at the lower part of this slide, was deployed off the research vessel Sharp, and a target field was then constructed in front of the field of view of the sonar. On the rail system, we have a tower that could travel along the rail at 5 meters a second, and every half second it would ping, and allowing us to collect sonar data that is sufficiently sampled to allow us to do synthetic aperture sonar. What I've shown in the center is an inset of a CAD drawing of what the sonar platform transducer configuration is for during the T-REX experiment. Importantly, the large magenta item is our low frequency receive array. The yellow item is a low frequency sonar that transmits our sonar signal. The green box represents a high frequency sonar, and then the receiver is not on this faceplate, it's elsewhere on the tower. These are in-situ photographs from the 3 different experiments that we have conducted. The top shows a 155 millimeter howitzer on the far left. It's a prowl target, meaning that it's sitting on the surface. We then have a picture of a partially buried target, which is a 105 millimeter solid aluminum replica of an artillery shell. Fully buried, of course, is just a picture of the sand-sediment interface. And finally, we have what we call obliquely buried, where the nose of an item is penetrating the surface, and so the tail is sticking up in the water column. BAYX occurred in a brackish water environment where there is sufficient runoff from nearby streams that you have a nice mud layer. So when we deployed targets, all targets sank into the mud layer. The larger items sank to come to rest on a sand sediment sub-bottom, and then the other items that you're seeing in the center for the BAYX and on the right are small enough that they actually sink within the mud layer. The mud layer does cause complications with both the data collection and when you come to doing the numerical modeling. The lower pictures are from the CLUTTEREX experiment, which is what I'll principally talk about today. And this is an experiment where we put out targets of interest, the 155 millimeter shell or the 105 millimeter shell, and then clutter objects that are principally the same size that you may find in a harbor environment. In the left picture, that's a scuba tank sitting next to the shell. The center one shows a crab trap. And on the right, we have a construction center block. For CLUTTEREX, the way we constructed the experiment and the picture on the right, the rail system runs from left to right at the bottom or right to left at the bottom of the screen, and we can then deploy targets anywhere within this 40-meter by 40-meter box. And the way the pyramidal structure of the target layout is determined is we want it to have fully focused SAS imaging. In the image, the blue dots are target locations, and the red triangles are where we put a clutter item next to an object. So you can see in a single target field, you could have close to 68 targets at a time. For our targets, we had 20 science targets. These would be spheres, solid cylinders, cylindrical pipes, flat plates. There were 10 man-made clutter object types. There are replicas of those types, but we had scuba tanks, 35-gallon drums, the center blocks, just various items of about the same size of the shells we were looking for. For the CLUTTEREX experiment, once a clutter object was put down, the divers did not touch it, but the divers did go in and manipulate the target so that we could get a full 360-degree look at a target, so we could fully populate what are called acoustic color plots, and I'll get to those in a few minutes. One unique thing about both the T-Rex or both the BAYX and the CLUTTEREX experiment is that we were able to simultaneously transmit both high and low frequency signals, which allows us to generate high frequency and low frequency SAS images that are co-registered. What I'm showing here is three examples of the high frequency and three examples of the low frequency synthetic aperture sonar results. The top row is high frequency, the bottom row is low frequency. The number that you see in the top right-hand corner in any one image is the orientation that the divers had tried to rotate targets to. So in the left column, the targets are at 0 degrees. For us, that's broadside, meaning that the axis of symmetry of a target is aligned with our rail system. The 20 degrees now is just a 20-degree clockwise rotation, 40-degree clockwise rotation from being in the broadside orientation. And you can see that the orientation of the target is important. If we look at just in the high frequency, for example, this pair of clutter item and target, when the target is rotated to 20 degrees, we start to lose the target response, whereas the clutter item was not manipulated by divers, is still strongly seen. And as you go to 40 degrees, its response is completely different than a 0 degrees response. And that response dictates what we see in our acoustic color response. For most of what we do, we try to do our classification on the low frequency synthetic aperture sonar data. And so I'll be mostly talking to the remainder about the low frequency response. Before I leave this slide, I do want to point out that the horizontal lines that you see in the high frequency images, those are very thin ropes that were stretched across the target field grid so that we can get a spatial grid with 5-meter separation that the divers could align targets to. The other thing is you can see a pronounced sand ripple field in the area that we were operating. The sand ripples do not show up, or they show up very weakly in the low frequency sonar data. So what we did in our CLUTTEREX experiment, we took data with just a target in the target field. That's the top row of images on the left. We took data with the target and the clutter item in the target field. That's the center column of SAS images. And then we removed the target and just took synthetic aperture sonar data on the clutter item itself. The left column of images is the high frequency, and again, you can see the sand ripple, and you can also see the rope that the divers use to guide themselves underneath the water. The right-hand column of images are the low-frequency images. Now, if you take the time signals that are used to generate the SAS image, and instead of generating SAS imagery, which is a spatial view of the target, and instead convert that into a target strength as a function of a target aspect angle and frequency, you get the 4 plots that are on the lower right-hand side of this slide. Now, if you look at the plot labeled T, that's the target by itself. And this is a 360-degree view of that target response in frequency space. If we now look at the one that's the next one over, which is labeled T plus C sub large, that means we've taken the time signals that were used to generate the image that's in the red box and just simply converted them into an acoustic color plot to see what we got. Here, you are not trying to distinguish between what is the target response and what is the response to the clutter item. And you see that this image does include information about the target, but there's a additional structure in there that can have profound effects on how a classification or even a detection algorithm may work. What we then tried to do is, with the little yellow box that or whatever that is, a pentagon, that we have placed in the windows, we tried to spatially filter out the contribution to the clutter, and that gives us the third column of acoustic color plot, where we're now trying to say, okay, we want to separate targets and just recover the target of interest. And if we just visually compare the first and the third acoustic color plots, you see that we have been able to recover quite a bit of the target by itself response. There is some differences at the resolution on this screen. It's a little bit harder to see, but in the off axis or off broadside or off end on orientation, we see that the structure has changed. One thing I guess I ought to tell you is that at 0 degrees is broadside, so that you're hitting the side of the cylinder, and the principally 180 degrees and 270 degrees that you're hitting the solid cylinder tail on. The final panel is we've taken the time signals that generate the low frequency synthetic aperture sonar image, and we subtract those time signals from the companion image. So we're trying to remove the response of the center block here from that of the target. And when we do that, we get the last column here, which is the large box minus the clutter only box. When we do this, we see that we can again recover quite a bit of just the target response, but there is still what we see in the image, some structure that remains. And this structure, because of its periodicity, suggests that there may be a multiple scattering issue going on. That is, sound scattered from the target interacts with the clutter object, and the sound scattered from the clutter object interacts with the target. And that cannot be removed by a simple subtraction technique that we tried here. All the data from the T-Rex, BayX, and CLUTTEREX have been isolated. So each one of these little spots in this image, we have gone in, we've cut up the part of the time signal that makes the image, and we've put it in a data repository, and I've written a MATLAB GUI that goes along with that data repository, so anyone that has access to the data can then explore the response of the target. What I'm showing at the bottom here is a screenshot of what the MATLAB GUI gives us. The left-hand column is the isolated time signals. If you convert those isolated time signals into the acoustic color domain, that's the center panel, and that's just a small portion of the full acoustic color template, which is showing on the right-hand side. The data repository is available upon request, and you can just send me the request, and then I'll contact people to make sure that we can get you to the data. that was the experimental part of our basic research, and I'm going to quickly go over the modeling aspects of our work. Our experiments provide both data that we can use in developing classification algorithms, but they cannot provide sufficient data to cover all possible environments that we may want to operate in. And so we want to develop models that can be validated by data, but then provide synthetic data to augment the development of classification models. The first model we use is called a hybrid model, and it combines finite element modeling for target response with a Helmholtz Integral for propagating the scattered sound to some distance. And I apologize for equations, but being a technical person, I don't seem to be able to put together a talk without an equation in it. What I'm showing in the bottom is a 105 millimeter artillery shell in the computational finite element domain that we use to generate the pressure and normal derivatives of the pressure on its surface. We then use the Helmholtz integral to propagate it out to the free field. This model has been benchmarked against other models that use different approaches, and we consider this to be what we would call our high fidelity exact model. That model, when we originally started using it, was somewhat slow, and we wanted a fast way to generate a lot of data. And we came up with what we call the TIR model, the target and the environment response model. And this model makes several assumptions to principally collect the scattered field from a target within any sort of environment that you can place the target and try to maintain high fidelity in the answer. In its simplest form, you convert what we call the waveguide scattering problem to a collection of free field scattering problems by using image sources and receivers. The equation I'm showing at the bottom, the takeaway message is that you have a propagation component from going from the target, from the source to the target. You have a component propagating from the target to the receiver, and you have a scattering amplitude. The scattering amplitude includes all the information about the target itself, its material properties and its geometry. And it's that's important for driving the TIR model. So to drive the TIR model, we want this free field scattering amplitude, the quantity in the red, and we obtain that from the hybrid model by propagating the acoustic field to a far field from the target onto a hemispherical or spherical surface. And once we have that scattered pressure, we can use these simple formula to construct lookup tables for what the scattering amplitude for any particular target is. We have scattering amplitudes for 12 or 13 individual targets that we can use. As I said, we want to augment the available experimental data. So we've done some TIR simulations where we considered a linear SAS system that spans 50 meters, which is a little bit longer than our experimental data, but that's okay. We're just trying to generate raw data snippets. We put 12 targets and 2 clutter items in the target field on each side of this simulation. There were 14 horizontal ranges where we placed a target at different locations within the target field. We had targets visit all ranges. We, again, manipulate the targets as we did in our experiments. We rotated them through 180 degrees if they were symmetrically symmetric targets to try to get a full acoustic color template. And the most important thing in this simulation type of environment is we could look at 14 different environments. Our experiments were done in mud and sand. With the 14 environments, we could consider mud, silt, sand, cobble, rock type bottoms. That's important in getting the reverberation contributions to the signal, as the TIR model only computes the target response. If you do all the math, we came up with 882 data sets for additional data that we could augment our experimental data. With the number of items we put out, you end up having 12,384 independent objects. So we've expanded the data set that we can use for doing training and training of classifiers. I do want to acknowledge Denton Woods from MSWC Panama City. He provided reverberation backgrounds using a ONR funded model that Panama City runs. What I'm showing here are just 4 of the data samples for a particular target, a 2-foot long, 1-foot diameter aluminum cylinder, where the bottom has changed, but the target has not. And you can see by just comparing, say, the fine sediment one in the upper left to the coarse sediment one, or the coarse sand one in the bottom right, that the main response at broadside is there. That's the really bright spot. But the off-axis elastic response is being masked or altered by the reverberation that is in the environment. So we have this data, and we want to train classifiers. We want to be able to say something more than say, oh, we found something. We want to be able to say what we found. Under the MR 2505 program, the classifier that we look at is a Gaussian mixture model. An important aspect of the Gaussian mixture model is the generative classifier, and this means that you generate a model for each individual target itself. This is different than, say, an RVM or an SVM, where those are discriminative classifiers, and there you train a single model using information from all the targets in the collection. The way we generated our Gaussian mixture model is we used an L2 norm. That's just a separation distance in the vector space. And the vectors that we sampled, if you look at the lower right-hand panel, you see 2 acoustic color plots, and the vertical or the horizontal lines going across is where we sample the vector. So we're sampling a specific angle through all frequencies, and we sample them in a random order. So we throw away the fact that there is some information in the angular space, but we're more interested in the frequency space. For those people that aren't familiar with it, the equation here is a generalized Gaussian, where X is the spectral vector, one of these white lines in the acoustic color plot. Mu is the mean spectral vector, which means we've averaged the vectors, and the capital sigma is a covariance matrix. If we take all of our synthetic data and we run it through the Gaussian mixture model, we can do different types of classification schemes. One is a binary classification. You're just trying to say, is this a target or is it a non-target? On the left-hand side, we have the rock curves that are generated from that type of classification. It's the probability of false alarm versus the probability of detection. And obviously, you want to drive this up to having 100% detection and 0 false alarm. So you would like to have a step function here. And what you see are the different color lines represent the different types of environments that we looked at for the classification. The right-hand panel, we now look at what is called the multi-class problem. Not only did we say, do we have a target versus non-target, we're now saying, can we take the targets and split those targets into, say, 155 millimeter versus 105 millimeter targets. And so we actually do see an improved performance with the Gaussian mixture model when we go to a multi-class type problem. Another way to look at these results is through what are known as confusion matrix. And I've shown the 2-class problem, that's the binary classification problem in the top portion of this slide. And the lower portion shows the 4-class problem. So this is a multi-class problem. The top row shows environment 1, environment 10, and environment 17. And the 2 classes of objects in these studies were 100 millimeter shell versus 155 millimeter shell. And with environment 1, which corresponds to mud, we see that all of the test samples for the 100 millimeter shells were actually classified as 100 millimeter, and all the test samples for the 155 were classified as 155, which is a good thing. But when you move to environment 10, which is a coarse sand, you start to see that there are some misclassifications that, for example, 400 millimeter shells were misclassified as a 105 millimeter shell. And as you go over to environment 17, which is a rocky bottom, you again see that how well you are doing with classification versus misclassification. Now, when we get to the 4-class problem, you're now trying to make a statement of not only are they targets, but what kind of targets they are. And here again, we are showing the how well we have performed in 2 different environments, a mud environment and a sand environment. The mud environment turns out to be fairly, I don't want to say easy, but it's much easier than environment 10 and getting the classification correct. And principally that is the reverberation in environment 1 is less than the reverberation in environment 10, or therefore the signal noise ratio is better in environment 1 than environment 10. So to conclude part 1, and I know I rushed through parts of this, I'm trying to cover 10 years of research. When the clutter objects are close to targets of interest, target signatures from the clutter item may be compromised by multiple scattering effects. The environment, and in particular the scattering geometry within that environment, affects the measured target strength. I didn't go over it, but as you change sediment properties, you change how the acoustic field interacts with the sediment and possibly reflects off and hits the target. And so you need to include environmental effects in your modeling to understand what you might actually observe in the real world. And finally, we looked at the Gaussian mixture model for a multi-class problem, and we think that this may aid in the discrimination of targets of interest from clutter. And so with that, I'll go to questions and answer, and I do know I rushed through a lot of detail, but 10 years of basic research, it's a lot to cover. So I'll open the floor.
Great. Excellent. Thank you, Steve, for the first half of the presentation. I'd like to remind our audience that you may submit questions for Steve by using the Q&A box at the bottom of the Zoom screen. We have received a number of questions. Steve, the first is from the Navy. When using the word classifier, do you mean a target or a munition type?
Well, to me, there's no distinction between the two. The classifier is you decide what is a target and what is non-target if it's a binary classifier. So if your target's 155 millimeter UXO, that is your target, and then anything else would be considered clutter or a non-target. If you're thinking in terms of actually, well, that's probably the easiest way. You decide what, given your data, you decide what you consider to be target versus what you consider to be non-target. And it doesn't matter if it's a big target. It could be a 500-pound bomb, or it could be a 55 millimeter artillery round. So it's up to how you design the classifier. I hope that answers the question.
Okay, that was great. Thank you. In your experiments, what are the limitations in the sizes of munition with your sonar system?
Well, with the high frequency sonar, if the target is proud on the surface, we can get fairly small. The resolution is on the order of centimeters, if not smaller, depending on the upper band of the high frequency. With the low frequencies, which what we really concentrate on, our frequency band is principally 1 to 30 kilohertz. And in our experiments, we had targets. We had an 81 millimeter shell that we could easily see, and we had targets that were on the order of 2 inches in diameter, and we could see those. in the environments that we were in. If you put those same targets, say, on a rocky bottom, you may not be able to see those due to the reverberation. So we're probably limited to maybe a 55 millimeter size target.
Okay, great. Is there natural clutter in the CLUTTEREX data set?
There are some rocks, or I'd actually have to look at the table. We had a palette of natural rocks that are about the same size of the 155 mil or the 100 millimeter targets that we had. Whether those all got deployed in any one experiment, I'm not sure. I'd have to go look at the log table. But yes, we had a few rocks that were available. We didn't have anything like coral heads.
Okay. What were the water depths for the site used for the CLUTTEREX evaluation?
The CLUTTEREX was done in 17 meters of water nominally, same way with T-Rex since it was the same site. That's nominally a 60-foot depth, and partly that is due to restrictions on divers, that if the divers go below 60 meters, they have to have rest days involved. And when you're at sea trying to get as much data as possible, you want to avoid rest days. So we want to keep the divers above 60 feet. The Bayx was 8 meters of water, so you have to worry about not only the interaction of the sonar with the seafloor, but you also have to worry about the interaction with the air-water interface.
Okay, thank you. How do you deal with multiple scattering, either experimentally or in the model? Do you separately consider multiple scattering in the sediment?
It turns out that I have just received funding about 6 months ago to try to include the multiple scattering within the tier model. We have a colleague at TNO that who has worked on putting multiple scattering in his hybrid model, and they've been able to show a multiple scattering effect between a target and the sediment interface. What I'm interested in is more the target clutter interaction, and we have ideas on how to put that in the tier model, and hopefully within the next year we'll have a first go with that.
Okay, excellent. Have you tried convolutional neural networks for classification of acoustic color data? And if so, how does the performance compare with the GMM?
I did not personally do the convolutional neural network classifier. My colleague Kevin Williams became aware of work that Dave Williams was doing at CMRE in Italy on convolutional neural networks. And Kevin tried to re-implement what Dave was doing and found it to be a very promising technology to look at. And in the slide where I was acknowledging Collaborators, I don't know if David Williams' name has shown up there, but we have given him access to our data and some of our simulations to run through his convolutional neural networks. And we think it's a very promising tool to add to our arsenal. We want to make the signal processing toolbox that I'll talk about in a few minutes modular to where you could plug in different classifiers to see how well they do and complement ones that are already there. Hopefully that answers the question.
Yes, I think so. Thank you. We have time for one or two more questions. First, does high turbidity cause interference?
If it's turbidity for like suspended sediment particles, it's certainly going to increase the reverberation, but we have not found that to be a problem in the areas we worked in particular Bayx. Our divers had, on a good day, 3 feet of visibility. On a bad day, they couldn't see the hand in front of their face, and we were able to collect data there. A worse problem that we had is when you put a rail system, a fixed rail system on the seafloor that's pretty barren, like in the CLUTTEREX, it becomes an artificial reef, and you attract quite a bit of fish. So you're now trying to to project sound through a cloud of fish, and it works, but you have to be aware of that situation.
Okay, thank you. And one final question, would you please comment on some of the assumptions that underlie the tier model?
The tier model was designed to be fast, but try to maintain fidelity of the answer. And so we make a far field approximation, which means that the targets are sufficiently far away from your source and receiver that you can throw away a lot of the mathematics and just assume very straight ray propagation ray models to the target. And likewise, we have to assume that the target is compact enough that, again, the receiver will be in the far field of the target's directivity. And we know that we violate that sometimes for our close range targets of, say, 5 meters. We know we're starting to violate these far field assumptions, but when we compare model results to data, we still capture principally the observed structure and the acoustic color. So that's one of the principal assumptions that allows us to generate speed in our model.
Okay, wonderful. Thank you very much, Steve, for answering all of the questions. We have received additional questions, and we will return to many of these in the second Q&A session. At this time, please proceed with the second half of your presentation.
Okay, for the second part of the presentation, I'm going to try to convince you that we're transitioning our basic research into an applied system. And what you're seeing on the title slide here is what we refer to as the MUS system, the Multi-Sensor Towbody system. It's a McCartney Focus 3 towbody where we have integrated both low and high frequency SAS systems on it, or sonar systems. To give you an idea of the size, that's one of our research engineers prepping to put the Focus 3 system onto the boat for its maiden voyage. So that's it's not a small system. The project team for the ESTCP project here, and I'm going to get tongue-tied today in MR18B4 5004, so I'm just going to call it the MUS system. Is Kevin Williams and Tim McGinnis, and we're going to acknowledge the vendors that were selected for commercial off-the-shelf parts because of the responsiveness and helping us get the system up and running. EdgeTech provided the low and high-frequency sonar systems, and McCartney Underwater Technology was the vendor for the Focus 3 towbody. Now, the technical objectives is to build and demonstrate the performance of a platform and detection, classification, and geolocation of underwater munitions. And if you remember the flow chart, way at the beginning of the talk, there was in the right-hand column, there was a project funded by SERDP that was MR2501, which was a design study on can we transition basic research into an applied system. And what you're seeing here is yes, you can. So what we want to address is the current lack of operational solutions, particularly for buried munitions. This has been a problem for as long as I've worked in the field, which is 35 years. How do you find buried objects near a water sediment interface? In our design studies and our basic research says that if we work in this 1 to 30 to 50 kilohertz range, we should be able to field a system that will work. So to date, the progress to date is indicated in this chart. The components were delivered at the end of 2018. There was a site acceptance step where the engineers from McCartney came to Applied Physics Lab, and our engineers and their engineers talked about the system, and we made sure that the system was capable to be deployed. The initial calibration of the low frequency sonar, which we refer to as EBOS, occurred in April. In July, the Applied Physics Lab dive team, along with the Pacific Northwest National Lab dive team, placed targets in Sequim Bay for a, it's not a blind testing, but a testing of the system to see that we can actually acquire data. A maiden voyage was done in Lake Washington to just test the navigational abilities of the tow body and whether or not our engineers could fly the tow body. And then finally, the Sequim Bay test happened in September 2019. And I'll principally be talking about results from the September 2019 test. What you see on the right is an actual picture of the EBOS system. The two EBOS sources generate 5 to 25 kilohertz band of sound. The orange structure in the center is the CLUTTEREX source that we use for our low frequency that has now been integrated into the tow body system. And then the long black panel here is a 64 element receiving array. When the initial design of the system was put together, only one of the two EBOS sources was conceived. And if we only had one source, whether it was on the starboard side, whether it was on the starboard side or the port side, we wanted to know how well could we resolve a target. And so what you're seeing along the bottom are 3 simulations. We have a port side, assuming the source was on the port side, and then on the far right is assuming the source is on, a single source is on the starboard side. And you can just roughly get an estimate, a feel for what kind of resolution you can get. We're trying to image a small scatterer, and that's that bright dot that you see here. But if you actually combine both images, or if you combine the use of both sources, you can then get the image that's in the center. So you actually get twice the resolutions by just simply adding a single source, a secondary source to the platform. On this slide, we're showing what we believe the seafloor coverage can be for the design of the MUST system. The design calls for the MUST to fly at a 5-meter elevation above the seafloor. And with that elevation, we should be able to have 15-meter separation between adjacent tracks when you're towing the tow body in, say, a mow the lawn type pattern. The upper panel with the green little triangles is a projection of idealized beam patterns onto the seafloor. And so you see that you get principally 18.5 meters of coverage with about a 3 to 4 meter overlap. So we know that we shouldn't miss a target with the low frequency in that case. Now this 5-meter spacing actually gives us quite a large footprint on the seafloor, as we have side scan sonars that are on the pontoons looking out away from the vehicle or the tow body. And we can get roughly 35 meters to 40 meters of coverage on any one side of the platform, and we get triple coverage with a 15-meter spacing. What I'm showing here are demonstration criteria, and this chart is drawn from a workshop that SERDP conducted on if we're going to go out and do a munitions response task, what do we need? And so 3 of the tasks that came out of there was detection of all munitions of interest. These are the objectives. You want location accuracy and you want production rates. That's the left-hand column. So for us is what are the metrics? So it's the percent detected and correctly classified for the detection of interest. The metric for location accuracy is, of course, what is the average error and standard deviation and locating an actual item. The production rate is how big of an area can you survey in a day. The data requirements for each of the performance objectives are listed, and then off of this chart, really the principal thing is what is the success criteria? And for us, the success criteria, and this is in the document, is you want to have a probability of correctly classifying a target of greater than 0.94, while you have a probability of false alarm less than 0.1. And we want to achieve up to a kilometer per day of survey size so that you can cover a fairly large area in a day. So what this criteria would mean, if you have a target field that contains 50 munitions and 50 clutter items, that probability of correct classification would say that you have missed 3 munitions out of the 50, while at the same time the probability of false alarm would say that you've taken 5 clutter objects and have mislabeled those as targets of interest. And of course, that now is a trade-off in the expense of actually carrying out a full remediation of recovering the items or doing something to neutralize or remove the hazard. So for the Sequim Bay test that occurred in September 2019, what I'm showing here, we're in an average water depth of about 20 meters. It's a relatively flat bottom, and it has a couple of sediment types. And it turns out that right about here on Sequim Bay, Pacific Northwest National Laboratory, it's a DOE facility, has a dock and laboratory facility that can be used for staging experiments out of, or that's principally it. You can stage experiments out of their facility. So prior to the Sequim Bay test, the Applied Physics Lab dive team and PNNL dive team spent 4 days laying out 2 different target fields. And the target fields they laid out, one of them was in a sandy site and the other one was in a mud site. And what we're showing here is that they laid out a center line, and off of the center line, they laid out specific targets in roughly 5 meter separation, so that we would be able to run over the target fields in 2 environments and see how well we perform, where we actually know where everything is at and everything is labeled. So some comments that preface this Sequim Bay test is the original receive panels that we received from EdgeTech was using a new technology to build the receive array panels, and it turns out there was a manufacturing flaw in the panels, and so their sensitivity would start to fall off. EdgeTech was responsive and got us new panels a week or so before the test, and so we had to get the panels onto the system and integrate it with everything we had before the test. The goal of this test was just to get data from the targets in the clutter in 2 different sediment areas, and we wanted to use this data to further work on synthetic aperture sonar development. In particular, we're imaging volumes now, and also to start to think about how to modify our classification codes to accept the data type that we will be receiving on the MUST system. And what we conducted was a 4-day effort covering those 2 target fields. And so the next couple of slides, I'm going to step through some of the details of doing the Sequim Bay test. So on September 9th, well, in the center, we see the black box, and that's where all the testing was done, was someplace within this black box. On September 9th, I'm showing the GPS tracks of the ship that towed the tow body, where we're principally going over the sand target field. September 12th, we then went over to where the mud site is and went over the mud field quite a bit. We also looked at the sand site. September 11th, I actually indicate where the sand site is and where the mud site is. We again collected additional data. And finally, on September 12th, what we're showing is we have a area of almost 1 square kilometer that we're covering, which means we're almost meeting a design criteria objective of covering 1 kilometer a day. What I'm showing here are the high frequency side scan sonar images of the Sandy site. The top image on the left is a broad survey where we're just looking at what is in Sequim Bay, and then the bottom image is just looking principally at the mud site. The right-hand image is showing the target line on the mud site. The red dots at the top and the bottom of this image are stakes of holding the center line. And then you can see, for example, a target here, which is probably a square lobster pot. And some of the other targets you might be able to see, other ones are harder, so you can see this target up here. In the mud site, the larger targets sink into the mud, which means that you're not going to really see the targets in the side scans, a high frequency side scan sonar, because it can't penetrate into the mud. Again, here's high frequency side scan sonar images of the 2 different target fields. The left-hand one is the sand site, the right-hand one is again the mud site that I just showed. And you can easily see the targets in the high frequency side scan. Here's the target, here's the target, target in the sand site. And so in trying to work out imaging algorithms and detection algorithms, because the mud site appears to be a much harder site, we've been concentrating on, can we understand the data we've collected from the mud site over the sand site? The assumption here is in the sand site, many of the targets will be proud and we'll be able to easily detect them in the high frequency sonar. So the EBOS, again, is the low frequency sonar, and I'm going to consider the mud site. There's 2,000 pings in a data set. We can get 120 degrees of integration angle, and that's real aperture. That's the cross range. We get 90 degrees of integration in the synthetic aperture processing. So as we move forward in space, we are creating synthetic aperture images in the long track direction. With the 2-source configuration of the EBOS, we alternate ping. So we ping from the left source and then we ping from the right source and so on as we proceed down the track. For our imaging algorithm, we are now using a fast factorized back projection imaging algorithm. And a nice thing about that is we've been able to put that algorithm on a GPU, which greatly enhances the processing of the data. We are now not creating just a synthetic aperture sonar image, but we are imaging a volume. So we now have 5 by 5 by 5 centimeter voxels in a volume. And this could be undersampled. Part of it is a memory restriction on the computer system that we were using at the time. We hope to be able, and I think we have, I'd have to talk with Tim Marston, one of the people working on this. We've been able to reduce the pixel size and update our imaging system. So what I'm going to show you, and it's going to take me a bit to explain this, are maximum intensity projection images. The top row, or the top panel, is an image in the mud-water interface. And what is done is any slice in the volume, so this is a slice in depth, you take a line and you run it down through the volume and you say, what is the maximum voxel intensity? I'm going to take that maximum voxel intensity along this line and I'm going to project it into this interface. So this little dot here could be this little dot out of this slice. And you can do a maximum intensity projection image on any surface that you want, but again, you're looking through the volume for a maximum pixel. Now, this image is from the mud track, and we know that there are a dozen targets out there, but you don't see any targets at all in this image. And so the question becomes, where are all the targets? Well, you're projecting a maximum intensity voxel into that image. It turns out that if you project these voxels, you have a sediment layer that you have that is a bright, it's a bright feature in this volume image, or you have discrete scatters. You have a bunch of discrete scatters. The scatters could be shell hash, could be small rocks, it could be debris that has come in from water runoff. But you also have the targets that were placed in the mud, and you also have the mud layer that you see in this slice through the volume. And so if you choose the maximum pixel, say between these two depth locations, you're going to be picking out that guy, you might be picking out this guy. And so you've washed out the ability to see the images. So the question now becomes, can we find a method to find the targets within this voxel? Well, if you simply start to decrease the volume over the depth over which you're picking out the maximum pixels, then of course you can, because now you're beginning to ignore the layering in the sub-bottom. And if I flip back and forth between these two images, you can see that the signal to noise is improving in that upper panel as we go down. So if I move that line up a little bit higher, you start to pick out the targets now begin to show up, because you're now removing essentially noise creating or volume scatterers that are contributing noise to the data. And finally, if you come up to where you're only considering a very thin layer, you can find all the targets that are in the mud. One thing that you also see when you're looking at these maximum intensity projections is you can't remove the mud glint. This right here is you're basically looking straight down at the mud, and you always get some surface return that's going to be fairly bright. And so this actually can help you kind of register where you are in space that you're looking down, and this is the center line of the toe. What we're currently working on in our software interfaces, allowing the user to adjust the depth through which they're looking at when they're creating these maximum projection intensity, called MIP image. So we're now going to look at the volume rendering, and I've numbered several of the targets that we've just seen on the last slide. And we're going to look at what is the volume image looks like when we consider trying to isolate each one of these targets so we can extract data for the classifier. So this is one view, and then the next slide we're going to change the view, and the next slide we're going to change the view again. So in these three slides, you can actually start to get some idea. You can actually start to get some idea of the size and shape of the object just by looking at the different views through the volume rendering. And someplace. So what we have done and where we're at in the status of using the MUS system to acquire data and then take that data and convert it into acoustic color so that we can put it inside our classifiers. What I'm showing here on the left in the upper, this is the acoustic color for a 2-foot by 1-foot aluminum pipe obtained in Bay Exel. This is a pipe that was in mud. And then on the right-hand side is the CLUTTEREX17 cement block data acoustic color plot. The lower set of images are attempts of extracting data, converting them to an acoustic color, and just simply comparing them with what we just saw in previous experiments. Now, I'll note in the lower panels, this is just a straightforward, we're taking the time signals and doing FFTs and looking at angular space. These are not normalized data sets, so there's no correction for circle spreading, and there's no correction for beam patterns for the receiving and source arrays. But we do see that we are able to extract data that principally looks like the aluminum pipe from the MUST system. So we think we can adapt our current classification schemes and use it with the MUST system. And again, the cement block, we pick up structure in the MUST data that we see in our CLUTTEREX data. So there's several lessons learned from this first Sequim Bay test, and the first is the acoustic color generation, the high resolution patch imaging is currently under development, and we're trying to fix that. Like I said, we've put some of it on a GPU, which greatly enhances the ability to process the data. In fact, I've been told that we are almost near real-time processing with the GPU. What I've showed you in the previous slides, this is all based on the MUD site, because MUD was a harder environment. The targets sink into it. Now you have to deal with, you can't actually see the targets easily on the surface. The third bullet down is we're working on our beamform, and we can do it. In fact, I forgot to mention, all the imaging that was previously done was just based on using the GPS coordinate location of the tow ship and then knowing what the payout was to the tow vehicle. That does not include any inertial navigation unit information from the tow body itself. As I previously said, the acoustic color hasn't removed any spreading loss or the directivity of the sources and receivers. But we think we're getting about 40, plus or minus 40 degrees, so we can cover that 15-meter swath that we hope to cover. The EBOS panels that we received to replace the ones that initially failed work nicely, and EdgeTech is actually preparing a new set to improve upon what we have on our current system. Because of when panels have arrived and when we can get them on our calibration facility, some of the data, it's good data, it's just not calibrated data. It allows us to at least see how the system's performing without worrying about, do we have absolute calibration. The handling of the vehicle will require 4 or 5 people once this vehicle or the tow body goes from being an experimental platform to hopefully a commercial partner. And we're putting quite a bit of effort into making the interface for the system. How do you fly the tow body? What kind of feedback do you get? We're putting a lot of emphasis in making it a user-friendly signal processing package, and then one that a user could potentially, it'll be modular, so a user could potentially add a signal processing module of their preference to the system. So the benefits to the DoD is that we've tried to integrate the basic research that we've worked on for the past 10 years into a system that we believe can be deployed and address underwater munitions remediation. One thing I didn't get into detail is the MUST system was designed to carry more than just the low and high frequency sensors that APL considers. If you're in an environment that has sufficient water clarity, it would be possible to put it on laser line scanner system or a LiDAR system, just a camera system, that there's sufficient power and communication bandwidth going down the tow line into the system that other sensing modalities can be added to the tow body. Another thing I didn't really cover is we tried to minimize what is in the water, and part of why we did that is it minimizes the risk of loss. If the tow body strikes an underwater obstacle and is destroyed, you're only losing the sonars, the INS units that are on there. The principal electronic packages are up on the ship and should be safe from being destroyed. And finally, there's a blind test scheduled for the third quarter of this year. The last time I talked to Kevin, they still hope to have that blind test. I believe it's in the August timeframe, August or September timeframe. PNNL will deploy target fields. At most, they might tell us where the target fields are, but other than that, we will have no idea what targets they place, have no idea what the orientations of the target. No information on the target field will be given to us, and we will see how well the MUS system can perform in that blind test. Here's some citations that I added to really cover principally the modeling that I kind of glossed over. Feel free to ping me and I can give you these citations, or look up at the YouTube or the webinar on the SERDP website to find these citations. And did I miss one? Oh, yeah, I guess I skipped this one. Feel free to contact me at my email address. I'm fairly responsive at odd hours. In particular, if you're interested in access to our data repository, send me an email and I'll contact the right people to make sure we can get you access. So we're up to the questions and answers on session 2. Hopefully the questions are easy, as I'm not directly involved with the manufacturing of the tow body. I just am interested in getting it out there.
Okay, sure. We have received a number of questions from the audience on this second portion of the presentation. The first is from EPA. What was the smallest size target ordnance for detection in the mud test bed?
For the recent Sequim Bay test, well, it's kind of, they put a crab trap out there, which the trap itself is fairly large, but it's got a netting on it, which is almost invisible to low frequency sound. And then the structure is like angle iron. It's or rebar. It's not that, the underlying structure is fairly thin. As far as munitions, I think the smallest thing that they put out was 105 millimeter ordnance that would be of roughly 16 inches long.
Okay, great, thank you. Where will the blind test to be performed later in 2020 take place?
It will also take place in Sequim Bay in the state of Washington. The blind test part of it is that PNNL is going to be completely responsible for putting in the target fields. APL will not be told any information about what targets they put out, orientations, burial depths. They'll just say the targets are over there, go find them. At least that's my understanding of how the blind test will go. And I should point out that PNNL, I believe, had submitted a proposal to become a test bed site. So this site would be, for any technology pitched to ESTCP, a site where testing will be performed.
Okay, excellent. So far, what was the deepest item detected there in that bay?
I wish I would have had the backup slide. It turns out that Kevin has given the data to our colleagues, DJ Kang and Todd Hefner, and they've been looking at what kind of environmental information can you get about the sediment. And you can see in that data different layering, and the layers are anywhere from 1 to 2 meters below the surface. We think that we can see an ordnance up to 2 meters deep in mud just because of the attenuation loss that you'll have in mud. And in sand, it's a little bit less. and that has to do with the ability to penetrate the sand. So we think that we can see, in at least mud, an ordnance up to 2 meters deep.
Okay. Next, we have a question about the plots on slides 55 to 57.
Do you want me to back up to those slides?
Sure,
right.
That would be great.
Let's see if I can do that. I don't seem to have control. But go ahead and ask the question. I have a hard copy.
There it goes. Okay. Are those plots showing amplitude in the time domain or in the frequency domain?
Well, these are actually images. So this would be spatial domain, that the sonar signals, which are time signals, have been coherently processed to give, well, you've rendered a volume. So this is a spatial domain image. And then the last question about what you can see, you're looking up to 2 meters deep here, and you can see the sand layer at 2 meters deep. So we can see fairly deep into a mud bottom. The targets here were all placed on the surface and just sank in, so they're fairly shallow within the first half meter. But this is spatial domain here.
Great, thanks. What are the plans to integrate a positioning system into the Focus 3 MUST for geolocation of the blind seed targets during these 2020 tests?
Well, there is an inertial navigation units on the vehicle itself, so we can get very good positioning of the system. I have been told by Tim Morrison, who's been principally developing a lot of the signal processing part of the package, that if he limits his number of along track positions to about 60 and doing a SAS processing of a volume, that he doesn't need that information. He can just use the GPS information from the ship and still render the volumes, which means the Focus 3 system flies very stable underwater, that there's not a lot of motion, or not a lot of nephorous motion. Okay,
thank you. And I think we have one last question on the second part of the presentation. You had noted that the desired MUST elevation above the seafloor is 5 meters. Can you comment on how close the tow body can be to the seafloor and still get the data?
So the tow body could fly at a much lower, or have a smaller elevation off of the seafloor. There's two complicating factors. Is the closer you get to the seafloor, the less of a footprint of the sonar on the seafloor. So now your track spacing has to be smaller to cover a large area. But a more important thing is, as you saw in the very first picture, there was a person standing next to the Focus 3 system, and although it's a very stable platform, it does take a bit to respond. So if there's an obstacle protruding up out of the bottom and you're a meter off the bottom, you may not have time to, the vehicle may not have time to respond to avoid that obstacle. So we prefer to stay at that 5 meter range to give us our area coverage rate and hopefully avoid any unforeseen obstacles on the bottom. But in principle, you could fly the vehicle at a meter off the bottom.
Okay, thank you very much, Steve. In wrapping up our webinar today, are there any concluding remarks or one last message that you would like to leave this audience with today?
I think the concluding remark is that I live in a basic research world where I like to solve the problems or address problems for SERDP, but in the end, there needs to be a transition of, is this basic research helping solve the problem that SERDP is really interested in, and that is the munition response aspect, or the remediation. Can we go in to, say, that off the island of Villegas and remediate their issue of having UXOs in their water? And think that that's something that I know Herb Nelson's very interested in, and I'm sure Dave is also, is that there needs to be a transition of the basic research into an applied program, and then more importantly, can the applied program then move on to being a commercial, does it have a commercial aspect that we can actually field a system? And I think that's the important thing to think about.
Okay, excellent wrap up. I appreciate that. Thank you very much, Steve, for your presentations and answering the questions today. Our next webinar, yes, thank you. And our next webinar in the SERDP and ESTCP webinar series is on Thursday, May 7th in the Environmental Restoration Program area. And this webinar will focus on novel approaches to remove PFAS from investigation-derived waste. Registration is open for this webinar and other future webinars. So please visit the SERDP and ESTCP webinar webpage to register. Before we conclude, I would like to remind you that both the audio and a copy of the presentation of today's session will be archived on our webinar webpage in case you would like to refer to them in the future. We would appreciate it if you could please take a moment to complete the survey that will pop up on your screen at this time. This concludes today's webcast. Thank you.